Assalamualaikum warahmatullahi wabarakatuh. My name is Ilian Hakimiyah and my other teammate, which is Ayu Madiha, Nur Rafida, Reyes Izzati and Shelly Amanda. So we from Group 6 will be presenting our scientific inquiry article critic with the title of Home Energy Management System HEMS with Optimal Energy Management of Home Appliances using IoT.
This study introduced a cost-effective home energy management system that uses IoT data from appliances like air conditioners and refrigerators to reduce electricity use without needing extra sensors or complex setup. The system runs in 3 stages, which is parameter estimation, load forecasting, and optimal scheduling. Over a 61-day test, it reduced energy costs by 4.4% and worked well with simulated demand response program. However, it lacks real-time control, which limits its ability to respond to sudden changes. Forecasting errors, especially for refrigerators, with up to 13.25% error, and a limited number of controlled devices also affect accuracy. Still, the result shows strong potential for developing more accessible and scalable smart home energy solutions. The increasing demand for global energy, especially in residential sector, has made it essential to reduce household electricity use. This is largely driven by rising fossil fuel price, the growing electrification of homes, and the increasing stress on national power grids. In response, smart homes equipped with IoT technologies have emerged, offering real-time monitoring and control of appliances. Many studies in this area focus on advanced HMS setups that involve solar panels, sensor networks, and complex scheduling systems. However, most of these energy models depend on high-quality data, consistent energy infrastructure, and expensive equipment, which aren't always practical for regular households. That's why there is a clear need for a simpler, more affordable energy management system that can still function effectively within the limitations of typical smart homes. This study focuses on addressing that gap. This study focuses on 3 key questions. First, can we reduce home energy costs using only IoT appliances data without installing extra sensors? Second, can simplified control methods originally made for microgrids still work well in smart homes? And third, what impact does the proposed HMS have on overall energy use and participation in demand response program? These questions help guide the design of a more practical and affordable smart home energy system. This study uses a structured approach to develop a cost-effective home energy management system or HMS using only data from IoT connected appliances without requiring extra sensors or complex hardware. The first step is appliance selection and modeling. Air conditioners and refrigerators were chosen due to their high energy usage and IoT compatibility. Their behavior was modeled using historical data, applying techniques like nonlinear regression and moving averages. Next is load forecasting and scheduling. The system forecasts non-controllable loads hourly using IoT data. Then, a mixed integer programming algorithm is used to schedule the operation of controllable appliances while considering factors like electricity pricing, user comfort preference, and participation in demand response programs. In the prototype implementation, the system was tested in a real-world smart home for 61 days. It included modules for data management, parameter estimation, forecasting, and scheduling. Performance was evaluated based on energy use, cost savings, and comfort levels. Lastly, an economic assessment was conducted to evaluate installation costs, energy savings, and return on investment, ensuring the system practicality and scalability for everyday households.
For the results and conclusion, the article shows that the IoT-based home energy management system managed to cut energy costs while using fewer sensors. In the 1-to-1 case study, it saved about 4.4% compared to the baseline. The daily energy used was roughly 3.84 kilowatt hours, and the total cost went down to 52 cents instead of 54 cents. When a demand response program was added, the system showed a small extra profit of around 3 cents per day. User comfort was mostly maintained, with indoor temperature staying between 23 and 27 degrees Celsius. There were a few small errors due to air conditioner model. This study is still limited since it only used 1 test house and appliance from the same brand. The short testing period also didn't show long-term or seasonal effects. Even with these limits, the article gives a practical way to use IoT appliance for energy management without installing many sensors. For the limitation, the study only used one house, so the results can fully represent real homes. All the appliances were from the same manufacturer and connected to one IoT platform, which isn't common to everyday settings. The test ran for just one month, so it didn't show how the system performed over a long time or in different seasons. Another issue is that the refrigerator model has about a 13% error in power estimates, which affected the results. For future research, the authors suggest testing in more homes with mixed appliances and platforms. Running the study longer would also show how the system performs under different conditions. They also recommend improving the appliance models, especially for high-power devices like refrigerators. On a larger scale, they suggest looking at how the system can link with community energy network to save more cost and manage energy better. For the author's conclusion, they state that the IoT-based HEMS can lower energy costs while still keeping user comfort. Using IoT appliance data instead of many sensors makes the system more practical and cheaper to set up. The case study showed a real savings and also suggested it could work with demand response program for more benefits. The authors think the system can be used in the more homes because it doesn't need much hardware. They also admit there's room to improve, especially making better models for appliances like refrigerators and running the test for a longer time. They also see a chance to expand the system to control more devices and connect to larger energy networks, which could help both homes and communities use energy more efficiently.
The study proposes a three-stage structure for managing home energy, consisting parameter estimation, forecasting, and scheduling, while purposely leaving out real-time control because of unreliable data from IoT devices. This makes the system simpler, easier to implement, and more practical for homes with limited technology. It also fits the current reality where not all smart homes have stable or consistent real-time data. However, without real-time responsiveness, the system can adjust to sudden changes like unexpected appliance use or weather shifts. These kinds of changes can significantly affect energy usage, and ignoring them could lead to reduced efficiency or lower comfort for users. One way to improve the system would be to add light real-time features like event-triggered actions or simple manual overrides. These don't need constant data but would allow the system to react when it matters most. Overall, the design is practical and works well for basic users, but by adding just a bit of real-time flexibility, it could be even more effective, especially in homes where energy patterns tend to change day to day. Now, let's look at the forecasting part. The system uses a moving average method, which is simple and doesn't need much processing power. That makes it ideal for homes with limited tech or unstable internet and helps keep things affordable and easy to run, especially for non-tech users or those in rural areas. But the downside is that it doesn't adapt well to real-life changes. Sudden weather shifts, changes in who's at home, or someone switching on a few extra appliances can throw off the predictions. In fact, the study showed a 13.25% error just for the refrigerator, and the air conditioner wasn't very accurate either. These gaps could reduce comfort and lead to less efficient energy use, especially in homes where usage patterns change a lot. A better option might be to use smarter forecasting methods like machine learning or time series models. These can learn from past usage and adjust more accurately in real time. So while the current method keeps things simple and cost-effective, improving the forecasting model could make the system much more reliable in dynamic everyday environments.
Okay, so now let's look at our third critique, which is about the system, design, and real-world application. So one of the strengths of this study is that the system was tested in a real house. This makes the result more believable and shows that the method can work in daily life and not just in theory. So the next strength is that the design also followed a clear three-step process based on industry standards. This makes the system more reliable, and on top of that, it also uses data from IoT devices that were already in-house, which helped to reduce costs and make the setup easier. But there are also some weaknesses to this study. The first one, the test only lasted 61 days, which is quite short. This means that it may not capture long-term or seasonal patterns. Another weakness is that the study did not solve the issue of mixing devices from different brands, which is a common problem in smart homes. Lastly, the system may not work the same way in other households with different IoT setups or usage habits. So to improve these weaknesses, we suggested 3 things. The first one, to make the testing period longer to capture more patterns. Second one, to try it in different type of houses and to see how it works in various settings. And the third one, to add more appliances that the system can control so that it becomes more flexible. So in short, testing in a real house is a strong point, but more variety and longer testing are needed to make the system stronger.
So, to summarize the key critics of the study, firstly, the study has no real-time controls, which limit the system ability in occupancy, environment, or user behavior. It also leads to reduced adaptability, energy efficiency, and discomfort. Next, bit forecasting method. Simple moving average method was used to capture the dynamic energy usage but fails. Also, 30.25% prediction error in refrigerator usage undermine the scheduling accuracy. Furthermore, narrow appliance scope. This study only focusing on air conditioner and refrigerators, which ignoring other high energy appliances and limiting the effectiveness of the system. Lastly, limited testing condition. This is due to the fact that the study is conducted in one household using single brand of appliances. Also, short testing period hinders the effectiveness of the system. As the final reflections, the study can be counted as practical and affordable. This is due to the research utilizing existing IoT data, removing the need for new sensor or infrastructure. It also makes smart energy management accessible and cost-effective. Next, it is also modular and upgradable. This allows feature integration of features such as machine learning for better forecasting and real-time control for responsive adaptation. Moving on, this study has strong potential for more impact. It could be more effective with expanded appliance coverage and deployment across diverse homes. The study can also solve problems for smart energy management in the household. Lastly, importance of extended testing. More trials in real-world environments are needed, as this will help for system reliability and scalability across different usage patterns.